Alright, good morning. So right now we are going to go over 5.6/5.7, the last lesson for chapter 5. This really goes over properties of something called linear relations. We've gone over what relations are and different types of relations. Now we're going to go over that word linear there. And so it's going to be just analyzing these kind of linear relations because they're really important in sciences. And kind of every different type of science, you're going to be seeing this in the future. All right, and it's going to be analyzing kind of these certain types of graphs. So if you remember, we have 4 different ways to represent relations. I'm just going to grab this other paper here and show them really quickly. So we have the one, which is a set with squarely brackets, and then you usually have kind of brackets, an x-coordinate, comma, and y-coordinate. And then you have a whole bunch of these. And again, the x's are from the domain and the y's are from the range. So that's one way. We had another way which were like kind of 2 bubbles. And you'd put the domain on one bubble and the range on the other bubble. And again, the range means y and the domain means x. So these would be your different x values, your different range values. And then you show their relation by doing arrows from one to the other. Okay? And then, so that was the second way. A third way was an XY table. We're going to look at that a lot today, and its correlation with the fourth way, which was some sort of graph, where one was X and one was Y. Okay, so these two are kind of synonymous. This kind of table can make you able to draw the graph. Okay, there's actually another way, which is the same as representing this. I think we went over it last day, but it's an equation. Y equals 5x squared plus 6x minus 7. Just any equation also represents some sort of graph, okay? Some sort of curved graph. All right. So those are all the different ways to represent a relation. So now we're going to look at just linear relations. So again, relations, but what we're going to look at today is just primarily 1, 2, and 3, those ways of representing. We're going to forget about these 2 because they're kind of not as useful as these 3 when you master them. Okay, so which table represents a linear relation? Justify your answer. So what does linear mean? I'll give you an example here. We have a line here. That's a linear relation right there. I'm going to draw another one here, and that's a linear relation. So these are examples, and now I'm going to give you a non-examples. Non-example here. So you have a graph here. Here's a non-example. And here's another non-example. Alright, so if you see those 4 examples, can you deduce what linear means? Overall, pretend I drew that with a ruler. Linear means a straight line. That's all it means. That a ruler can mimic. So if I take a ruler, this is the easiest test you can do to see if something's linear. If I can take a ruler and it can represent the line, then it's a linear relation. It's a straight line where it has a constant rate of change. If I see these 2 non-examples, can I represent it with a ruler? Can I make them perfectly with a ruler? No, I can't make either of them perfectly with a ruler. I can make sections of them with a ruler, but not the whole thing at once. So that's what that's what that word linear means. Now it says, an example, which table of values represents a linear relation? Justify your answer. So we have 2 table of values here. And again, we know there's 5 different ways of representing linears. Our end goal is to get to graphs generally. But here's our table of values, and we know that it's an XY. This is called a table of values, XY. You see other letters there. They're just kind of in spot for the XY. You can always bring them back to relate to the X and the Y. And it's always X on the left, Y on the right. Okay? So if we analyze this, what happens to the C? When you go down a step each time, you're going to add by 5 each time. Now what happens to this y unit when we go down each time? We're adding by 9. One way to find out how much you're adding by is you just go 41 minus 32, and the difference would be 9. Same thing you could do here, 59 minus 50, and you get a difference in 9 as well. So every step I calculated it, and it's plus 9. So if you see this, we know linear means straight line, which means same y increase for every similar x increase. So that's how you look at it through a table of values perspective. Because it's not represented as a graph, it's not easy to see. You can't just take a ruler and see if it lines up, because they're just numbers listed. So what you can see it is the same y increase for every similar x increase. So these are similar x increases because they're always by 5. And you can see that they're the same y increases all by 9. It doesn't have to be the same number as the 5, it just has to be the same on the same side. So this is a linear relation because of this fact here. Okay, so you might want to box this, star this, or something to sort of remember that. Okay. What it also means is the same rate of change of y for every increase in x. Here we can look on the left side. Again, it goes up by 5, so that's a good sign. If it doesn't go up by the same number, you can't really analyze it on your x side. But here, let's look at this. 75 minus 0, this goes up by 75. 300 minus 75, this goes up by 225. 675 minus 300, this goes up by 375. And then last of all, it's 1200 minus 675, this goes up by 525. So if you look, different numbers. If you see a different number at all, we see it all for our different numbers, but if you see it just once, it means it's no longer linear. Everyone has to be the exact same. So not linear. Because there's not a same y increase for every similar x increase. Not the same. Okay. Okay, now we're going to go on to the next page. Graph each equation, then state the equation, what it represents in linear relation or not. So again, there's 5 different ways that we've seen to represent relations, or a relationship between 2 variables. So here we have this equation. Right now in grade 10, I don't think you know what any equations really look like. Okay, you analyze certain ones as you go along, but this is our first time seeing this. This is a relation there. That is a very concise way to show a relation. So let's see if we can go to a graph version so we can visualize what this looks like, because it's just a bunch of numbers and an x and a y, which you don't really know what that means. So how you do that, in every example, whenever you get a question like this, since the equation form is so hard to read, you draw a table of values for every question. And what that means is just a t-chart with an x on the left and a y on the right. Okay. So what this means is for every single x value you can possibly think of, all real numbers, if you multiply by -3 and add 25, this is the corresponding y value. That's what it means. I know that's a lot of words there. But what you do in this instance is you don't choose every x value and then try to times it through every time, because that would take a long time. You could, but you'd be here all day. So what we do is, what I do is I choose -3, -1, 0, +1, and +3 as your x value. And this makes it so that you can get a picture of what it's going to look like, and then you can deduce overall what you think the graph will look like from those 5 points. Okay, so let's plug in -3. -1, 2, 3. It'll be here on this line somewhere. Where on that line will it be? I don't know. I don't have a y value. So let's find out what that y value is by plugging this x value in, where you see x in the equation. Okay, so the example here is y equals I just write it down, but instead of x, I write -3 plus 25. What this means is -3 times -3 plus 25. So it's going to be positive 9 plus 25 is 34, positive 34. So what I can do after doing that equation, I can put 34 over there for y. So it means that in this equation, if I plug in -3, I get positive 34. And that means in my graph, I can put a point for that. This really means a point, -3 comma 34. So -3 comma 34. I notice I don't have 34 lines, so I'm going to have to make the scale a certain way. So if I look at this, if I make it by maybe 5, 10, 15, 20, 25, 30, 35, 40, if I make the lines on the y-axis equal to 5 each, then I'll be able to reach 34. So we'll say this one's a 10, this one's a 20, this one's a 30, and so on. Alright, so I've done that, I've made my scale. If we look at my x-axis, we only go from -3 to +3, so I can make my x scale maybe 2 squares equal just 1 unit. 1, 2 squares, 2, 2 squares, 3. Alright, so those are my scales of the lines. Alright, so -3, 34, so let's go 1, 2, 3. -3 will be over here because I made my scale a little bigger. So 1, 2, 3. And then we have to go up to 34, which is right here. Alright, so we have -3, 34. That represents this point here. Now we have to do -1. What's the y value for that? Well, we have to plug in -1 where we see the x value. So I would do the same thing here. -3 times -1 is +3, plus 25 is 28. And you do it for every number. 0 times -3 is 0, plus 25 is 25. And then 1 is -3 times 1 is -3, plus 25 is 22. And then the other one is 3 times -3 is -9, and that will give us 16 there. Okay, so these are all points on your graph. So let's write each one in our graph, -1, 28. So -1, 28, 0, 25, 1, 22, 3, 16. And then after I draw my little points, I am going to just deduce and see if it's linear. So I take my ruler and I see if they will go through all the dots. And they actually do. They go through every dot in a line. So I'm going to assume it's linear after taking my 5 points and draw a line. And then I can say that this equation means this line. Every single dot, if you can, a line is not just a line, it's an infinite billion amount of dots all together to make a line. Okay, so that's what this is. So we graph the equation, and it says then state which equation represents a linear. This does, so I'm going to say linear because I could draw it with a ruler. Now let's do this one, 2x squared plus 5. So again, let's go -3, -1, 0, 1, and 3. -3. We have to plug into this equation to find out what y value it has. So -3 squared is 9, positive 9, times 2 is 18, plus 5 is 23. Okay, well, I'll show you an equation form if you write it all out, because I do it in my head there, but sometimes you can't do it in your head. 2, we have to plug in -1 for the next one, squared, plus 5. -1 squared is 1, times 2 is 2, so it'll be 2 plus 5. 2 plus 5 is 7. So we end up getting a 7 there. And then 0 we plug in there, and we get 0 plus 5 is going to be 5. We plug in 1, we'll end up getting 7, and then we'll end up getting 23. Alright, so for this example here, I'm going to, since I don't have 23 spaces to go up, I'm going to have to scale it. So let's go up by, I'm going to say 3 each time. 3, 6, 9, 12, 15, 18, 21, 24. So that'll reach the max, so I'm going to say that's 24, and it'll go up by 3 each time. This case here, I'm going to go by 2's again, In this case, you could make each x unit just equal to 1. That would be okay too. -1, -2, -3. Okay, so -3 and 23, so that's going to go all the way up to like here. -1 and 7 is going to be -1 and 3, 6, 7 right there. 0 is going to be 5, so 3, 4, 5 right around there. 1 is going to be 7, and then 3 is going to be 23. Okay, so now that I put all my dots, you ask yourself, can I represent this as a straight line? Take my ruler, and I know I won't be able to go through every dot with a ruler. But I'm going to draw the graph anyways, what I think it'll look like. It'll look like that, probably. Alright, and then I'm going to say not linear, because it's not a straight line. Alright, this one. This one's a lot better. We'll go -3, -1, 0, 1, and 3. It's saying your y is equal to 5. It doesn't even look like an equation because there's no x in there. But the nice thing about this is saying it's y is always 5. That's what it means. Y is 5. So if I say when -3, what's y? Well, y is always 5. So I just say it's always 5. So now I can do each of these points again. -3, 5. This I'll just make each one worth 1. So -3, 5, -1, 5, 0, 5, 1, 5, 3, 5. And then I can draw a straight line here through all the points, so therefore it's linear. Alright, this next one is saying is x is equal to -4. What that means is x is always -4. So it's really the same as last. This time I don't go -3, -1, 0, 1, 3, because it's saying it can only be -4. So really it's any number, any number, any number, any number, any number. So it's saying x is always -4, so let's go 1, 2, 3, 4. Let's go there, and the y can be anything. That's what it means. It's kind of a fancy one. So I could draw a straight line this time, going through every point. So it is linear. If you go back to way back where it's saying, is it a function? If you look at it, the -4 value has like an infinite amount of y values, so this one's not a function. But all our other ones were. Alright, so that page is done. Now let's go to just some different types of questions to go over them. A water tank on a farm near Saskatchewan holds 6,000 liters. Graph A, is it filling up? Graph B, is it emptying? Alright, it's saying at a constant rate. Generally when you see at a constant rate, that usually implies it's linear. Because if it goes at a constant rate, that means it has to be a straight line because it's the same rate constantly. Okay, identify the independent and dependent variable. Our independent we know is the x-axis, which is time, and it doesn't depend on the other. And our dependent variable here is volume. It's the y-axis, and it does depend on what time it is. Alright, so that's in liters, that's in minutes. Alright, determine the rate of change of each relation, and then describe what it represents. So we have to go through what rate of change is. This is an important piece towards these types of graphs. So what is rate of change? It's change in y divided by change in x. So it's how much you change in your y values when you change your x value. Okay, so let's go through this. Rate of change is going to be, what's our change in y value? So what you do is you choose two dots, any two dots. You'll get the same answer no matter what two you choose. So I'm going to choose these two dots here. So if you look at this, our change in y values is we go from 1,000 to 3,000. So our change in y value is going to be the difference of those two y values, 3,000 minus 1,000. And then is over the change in the x value. So what x values do we change from? Still the same 2 points. We're going from 20 to 60. So we go the second one minus the first one. And let's calculate that. That'll give us 2,000. And then 60 minus 40, 20 is 40. And what are the units that we get? We have liters and minutes, because the top was our y, which is liters, and our bottom was minutes, which is minutes, or sorry, time, which is minutes. So now we just have to simplify this. 2,000 divided by 40. What does that give us? That gives us 50, and it's still the same unit, liters per minute. So what that means is it's increasing at a constant rate of 50 liters every minute. Okay? And you'll find that it's really important down the road. It's finding that rate of change. Change in y over change in x. Now let's do graph B. So rate of change. Again, it's change in y. So let's choose 2 points. You always have to do that. Let's choose this one and this one. So rate of change, we go from 4,000 down to 2,000. So we take the second one on the right, and we minus the first one. So again, you read left to right. So your first one is this one, your second one is that one. So you go 2,000 here minus 4,000. And then here you look at the x values and you go 40. And this is going to be 20. So 40 minus 20. And this is going to give us 2,000 minus 4,000. It's going to give us negative 2,000. Over 40 minus 20 is 20. Again, we need units. So liters on the top, minutes on the bottom. And this will give us negative 100 liters per minute. So what this means is this is positive, so it's filling up by 50 liters every minute. And then it's losing water when it empties by 100 liters per minute. So the negative sign means losing water. So this means fills. This means it empties, but it empties faster because it's a bigger number. All right, so that's how you find rate of change. We'll be doing this a lot. Rate of change, rate of change. Change in your y over your change in your x when you choose any 2 points in a graph, but they have to be on that straight line. And you can really only find rate of change if it's a linear graph, okay? At least at this point. All right. So now we're going to go into section 5.7, which is just kind of interpreting or analyzing these graphs still. Okay, so we're going to go through just a few questions, examples. This graph shows the fuel consumption of a scooter with a full tank of gas at the beginning of a journey. Write the coordinates of the points where the graph intersects the axes. Okay, this is kind of a new concept. We're going to intersect the axes. So the axes is this dark one and this dark one here. Okay, we have the x and the y axes. So where does it intersect the axes? We see one right here and one right here. Those are the 2 points that intersect these dark lines. Determine the vertical and horizontal intercepts. Alright, so where does the graph intersect here? What point is this? Well, it's just 200, 0. That's what point that is. What point is this? The other one is going to be 0, 8. So we have the 2 points there that intersect the 2 axes. And then if it says determine the vertical intercept, it's what when the y is equal to I should have lined up these differently, but that's okay. The vertical is when the y is equal to 8, and the horizontal, which means x-axis kind of, is when the x is equal to 200. This would be liters and this would be kilometers. Okay, so horizontal means the x-axis, vertical means the y-axis. So the vertical intercept is what y value does it cross there, and the horizontal intercept is what x value does it cross there. Alright, so we went into intercepts, and where it can intersect. Every line intersects both axes at some point. B, what are the domain and range of this function? So our domain and range we've done before, so this is just review. Our domain in this example, we go from, if I take my ruler and went across, remember domain is x always. So we go across, where does it hit first? There. Where does it hit last? There. Okay, so what x values does that represent? 0 and 200. Okay, so our domain goes from 0 to 200. Now we got to find range. 0 to 200, like that. Okay, another way you could write it is your x is in between 0 and 200. Now we go into range. What range values? Again, you take your ruler, but this time you go this way. You're going to hit it first there, and the last time it's going to hit it is up there. So it's going to be what y values? There first, and then thereafter. So it's going to go from 0 to 8. 0 to 8. So that can also be written like this. Okay, either work. So there's the domain and range of that graph. Okay. Alright, so now we're going to go through this sketching graph of the linear function this. So we have an equation and we have to put it in a different form to show the relation. Okay, this is already saying it's linear, so we know we're going to have a straight line, but what's it going to look like? We don't know. So whenever you see an equation, you always want to draw a table of values, x, y. And we're going to go from our -3, -1, 0, 1, and 3. I'm going to see what the y value is. So plug -3 in for there. -3 times -2 is +6, plus 7 is 13. -1 times -2 is +2, plus 7 is 9. 0 times anything is 0, plus 7 is 7. And then 1 times -2 is -2, plus 7 is 5. And 3 times -2 is -6, plus 7 is 1. Okay, so that's our table of values. We can now draw 5 different points. So our graph doesn't quite go up to 13, so I'm going to have to go up by 2's each time. 2, 4, 6, 8, 10, 12, 14, 16. So that'll be a 16 up there, and we're going by 2's. The x-axis I'll still go by 1's, though. Alright, -3 to 13. So 1, 2, 3, -3 to 13. 2, 4, 6, 8, 10, 12, and then halfway in between is 13. And then we have -1, 9, -1, 2, 4, 6, 8, halfway in between is 9. 0 to 7, 2, 4, 6, halfway. 1 to 5, 2, 4, halfway in between. And then 3 to 1. 1, 2, 3 to 1, which is halfway. Alright, now that I have all my points there, I'm going to draw my line. So that relation, or that equation, is exactly what I drew there. Okay, those two mean the same thing. It means that line. Alright, so let's go to example 3. Which graph has a rate of change of 1/2 and a vertical intercept of 6? Okay, so we have two graphs here, and we have to know what has the rate of change. Well, we know how to find rate of change. Let's do it separately for the two graphs and see which one has it. It's the change in y over the change in x. So in this one, we choose any 2 points, 1, 2, and from when you're reading left to right, this one, your left one's the first one, your right one's your second one. You go the second y value minus the first one. Okay, so So the second y value is 2. Your first one is 4. So you're going to go 2 minus 4. Change in x is down here. Your second one minus your first one, so 8 minus 4. This will give us a negative 2 on the top and a positive 4 on the bottom, and we can simplify that to negative 1 over 2. Is that a rate of change of 1 over 2? Almost. It has a negative though, so that's not. So that one does not. So I'm going to guess it's this one, but let's do it anyways. Change in y, let's choose these 2 points, 1, 2 here. So your y values, this is your first and your second, so your y value goes from 8, sorry, to 10. So we go 10 minus 8. And then our x values down here, we go from 4 to 8, or 8 minus 4. And this will give us a 2 over a 4, and we can simplify that to 1 over 2. But this time it's positive. What it really means is if it's positive, it means the line's going to be kind of aiming upward. And if it's negative, the line's going to be kind of aiming downward. Okay, but that's beside the fact. We can just calculate it like we did, and we see that it's this one. And it says, what one has a vertical intercept of 6? What does vertical mean again? Vertical means the y-axis. It means the up and down one. So it means this one and this one. So it says, which one crosses the y-axis at 6 is what it means. So does it cross at 6 here? 4, 6? Yep, that one does. How about this one? 4, 6. Yep, it's crossing at 6 there too. So they both do. So both have a vertical intercept at 6. Alright, one last question and then we are done this section. So example 4, this graph shows the cost of publishing a school yearbook for a college in Winnipeg. The budget for publishing costs is $4,200. What is the maximum number of books that it can be printed? So they put a few dots about where certain, I guess, companies bought a certain number of yearbooks. So one company spent $1,500 and bought 50 yearbooks. This one did $2,500 and bought 100 yearbooks. This one did $3,500 and bought 150 yearbooks. This one did $4,500 and bought 200 yearbooks. Okay, $4,500 to buy 200 yearbooks. So we don't have quite $4,500, so we don't know perfectly. So what we're going to do is we're going to draw a line that fits these perfectly. That goes through all the dots, like so. Okay, so if you notice, it doesn't really start at 0. It doesn't say it's $0 for 0 books. It's saying it's $500 for 0 books. So they kind of have a startup cost to this. But let's go through our example here. Let's analyze our line, and this will bring us to our answer. So how do we analyze graphs? There's just 2 different ways, really. What's the y-intercept? It's the important piece. So where does it cross the y? At 500. 500 what though? $500. Okay, that's the y unit that crosses the vertical axis. And then the other piece is rate of change. Okay, so rate of change we've just done. So we got to choose 2 points to calculate this rate of change. Let's choose this one and this one. You can choose any 2. So we have the first point and the second point because the first one is always the leftmost point. So here we go from 1,500 to 2,500. So we can go 2,500 minus 1,500. And then our change in x is from the same points, but down here we go from 50 to 100. So we can go 100 minus 50. And overall this will bring us to 1,000 over 50. What are our units? The y, the change in y is dollars. Change in x is number of. so dollars, and this is kind of textbook. So overall, we can simplify this. 1,000 divided by 50 is going to give us 20, again, dollars per textbook. So when we find this rate of change, it tells us that it's going to cost $20 for every textbook. Okay, but not when you're close to here, because when you've bought, say, one textbook, it's going to cost you over $500. So this is overall the rate of change, but it's not quite the amount you're paying for every textbook. How we can kind of analyze this is we need to bring it back to an equation. We've done equations to graphs, but now we have to go from a graph to an equation to fully do this. So overall, it's your y, which in this case is a c because it's cost. And if we use function notation, we can go cost when your x is n, when it's the n variable. So this kind of means like f of x, but this time it's c of n. And then generally when you do these, it's going to be $20 per textbook. So it's going to be $20 per textbook, which is the variable n. That's what it's going to cost, but it also has a startup fee. So generally when you do these equations, you have your y-intercept value, which you do first, and then you have plus your rate of change value, 20, and then you just write your independent variable, or your x-axis variable, which is n in this case. Alright, so once you do that, you get the equation for your linear function. But it still asks for max number of books. And in this case, it's going to be 40 CN, our cost that we're looking for, is 4,200. Cost of books is 4,200. And we write down our equation the way it is, plus 20n. And we have to solve for n, so we're going to minus 500. This will give us 3,700 equals 20n. Then we're going to divide by 20 to both sides, and we're going to end up getting 185 equals n. So the number of books for $4,200 that you could get is exactly 185 when you analyze this linear relation. We're going to do more on this in the upcoming unit, so this is just kind of an introduction, at least this question, for that unit. Okay, thank you.